Now once you have these confidences, then you can do all of that. I said whether pairwise ANOVA, I mean pairwise you want to not pairwise, I mean 2 sample or 1 sample, whatever we could do. Okay. When you do 2 sample, it is called Fisher's least significant difference method. There is nothing different from your 2 sample test. People give a jargon, it is called Fisher's test, but it does not mean anything. It is a jargon, it is same 2 sample test. Okay. When you do 2 sample test, whether these 2 means are equal or not, that is what Fisher's test is. After do an ANOVA, and if you do 2 sample, it is called Fisher's test. Okay. But it is the same idea. Okay. 2 sigma squared by n will become 2 MSE by n, okay, the variance. So you can give 2 sample test, etc. So now what else is pending is the power of ANOVA. We have talked about alpha. Remember, when we complete a test, we actually for 1 sample test, what did we do? We have fixed alpha, we know how to compute beta, right. Similarly, we now know to calculate, to perform ANOVA, to validate whether ANOVA is good or not for this case by looking at the the normality plot of the residuals, computing the residuals, normality plot of residuals, and also the variances. Okay. Then we know how to conduct 1 sample confidence interval, 1 sample test, 2 sample test, that we learnt. Now what is missing is what is the power of ANOVA. Okay. So power of ANOVA depends upon, like to compute the power of ANOVA, that is 1 minus beta. To compute beta, you should know the truth. If you do not know the truth, you cannot compute beta, right. If you, as we said, if the truth and if your sample is closely overlapping, then beta will be high, power will be low. If the truth and the sample is far away, then beta will be lower, the overlap will be lower, beta will be lower, 1 minus beta will be higher, right. So if your null hypothesis is 50, okay, mu1 equals to mu2 equals to 50, and your alternate hypothesis is mu is equals to 55, then it is easier because the difference is large. But if I say the null hypothesis is 50 and alternate hypothesis is 50.2, that is painful, that is the truth is 50.2, not alternate, the truth, we need to know the truth. Suppose your truth is 55 and your null hypothesis is 50, it is very easy to reject the null hypothesis because 55 is far away from 50. Suppose compared to, if the truth is 50.2 and your null hypothesis is 50, it is most likely that you will accept the null hypothesis even though if it is false, because the difference between the truth and null hypothesis is smaller. Okay, that is what the things become kind of tricky. If you are truth and if your null hypothesis are only small, the difference is very small, then it is difficult to reject the null hypothesis. But in reality those are the tricky situations, okay. But if they are far apart, then anybody could say, you understand. So that those are the tricky bits, and that is why to improve beta, I mean to reduce beta, the only way is to do what? If you do not change alpha, to improve beta, reduce beta, the only way to change sample size n, otherwise you cannot reduce beta. These are the things which we have learned earlier also, okay. So now coming to the power of ANOVA, you need to know the true value, and of course the true value, if it is close it is difficult to reject, but the key parameter that will determine your beta and your power is this factor that you have estimated in your treatments. I mean phi square, we call it as phi square jargon. Remember what is this? Your expectation of mean square treatment is sigma square plus phi square. This is the one which distinguishes it from null hypothesis. So the value of phi squared is the most important component. The more the value, the better it is, because your beta will go high. The second component is the most important factor, okay. So, your beta will depend upon phi squared and that will improve upon increasing n, which is natural, which again time and now you are seeing the same. If you increase n, your phi square will increase, beta will reduce and 1 minus beta will be better. Clear? So, in fact, there are some things called operating characteristics curves. I will not go over it. Okay. So, this is a function of phi and probability of rejecting the null hypothesis. Basically, phi squared, you have phi in the x axis, okay, and this phi is for various alpha values. Remember, for each alpha it will be different. So, you can have it for alpha equals to 0.001 and 0.01, which is 99 percentage and 95 percentage. And as your phi changes increases, the probability of accepting the null hypothesis will come down. That is, you will be rejecting the null hypothesis if it is false. If your phi is small, then probability of accepting the null hypothesis will increase, probability of accepting the null hypothesis will increase drastically even if it is false. This is probability of accepting null even if it is false. This will keep going high as phi decreases. As phi increases, this will come down, and phi is a function of n. It is a function of treatment as well as it is a function of n. So, if your treatment is very significant, you can do lesser number of samples, but that is nothing to prove at all. If the treatment is glaringly significant, you do not need hypothesis testing, right. You behaving normally and somebody hit you hard, then there is no way you are going to behave the same way. You do not need to do hypothesis testing for that, okay. But the subtleties are, if one person is around and if 3 people are around, is there a subtle change in behavior, whether this guy is an introvert or an extrovert, difficult to find when just small things change. That is where you need more amount of data points. So, when a person is to be modeled, okay, what are the different levels when a student comes in, you develop, or when you are interacting with the outsider, you have a model about him which is very easy to develop based on your interactions, very small interactions. But as you get closer and closer, what do you get to know? You get to know better the subtleties, and you will get to know the subtleties when you have more amount of interactions. So, whenever you want to distinguish between subtle things, you need more amount of data, otherwise your beta will go high and power will come down. That is what in a nutshell, okay. So far we have done what is called as fixed effects model, okay. Now the next natural step is to do what? Random effects model, okay. The random effects model, the model remains the same, but what is the assumption now? I am not interested in these treatments itself. Tau I itself is a subset of a bigger population. Earlier tau I was fixed, I is fixed from 1 to A. I am only interested in A treatments. Now this A is a subset of capital A. So there could be many possible treatments. I have chosen only small a treatments from the bigger subset, bigger set, okay. So fixed effect, the random effects model, your treatments itself is a variable and it is not fixed and it is a subset of the overall population, okay. So your null hypothesis will not be on treatment mean, that is a key fact. The null hypothesis cannot be on treatment mean because you are not interested in only specific treatments. The treatment itself is a subset of the treatments you have chosen is a subset of the bigger population. So that you are not interested in treatment means, rather my null hypothesis will be on whether the treatment has any variation in the overall data. I am not interested in this particular treatments, these are only a subset, but anyways does this subset influence the output, introduce variability in the data.
Is there an effect of any treatment which is a subset of the overall treatment? So, instead of telling the comparing the means, I am going to look at variance. So, my null hypothesis is going to be on the variation due to treatment equal to 0 or not equal to 0, greater than 0. Since it is a variance, it is always greater than 0. So, we have either sigma tau square equal to 0 or sigma tau square greater than 0. I do not no longer have the hypothesis on mean. Does it make sense? Right. So, we will follow the same procedure, but now it will be the hypothesis will be different. We will have the mean square and sum square treatments, etc. We look at it. So, that will complete our ANOVA, and from next class we will start looking at linear regression.